Black holes, among the most perplexing and unusual occurrences in the cosmos, continue to be a topic of exceptional analysis and fascination for astronomers and theoretical scientists alike. The astronomical entities, characterized by their immense gravitational strength and the complete lack of emitted light, signify a threshold beyond which established principles of physical science cease to function. Originally hypothesized by Albert Einstein in 1916, as a result of his general theory of relativity, black holes remained purely hypothetical until modern technology enabled their indirect observation. During the 20th century, a pivotal moment emerged in the 1960s when researchers examining the Cygnus constellation inadvertently identified a strange stellar body, a radiant blue star releasing intense X-ray radiation. This star, locked in orbit with an unseen partner, resisted conventional explanations until it was determined to be gravitationally bound to a colossal black hole known as Cygnus X1. The detection of Cygnus X1 offered tangible proof of black holes' existence and ushered in a transformative phase of research into these cosmic mysteries. Situated approximately 6,000 light-year from our planet, Cygnus X1 possesses astonishing traits. It is extraordinarily compact and produces a gravitational influence so powerful that even photons cannot escape. The hallmark feature led to the designation black hole, effectively capturing the essence of these enigmatic structures. Later investigations have identified an assortment of black holes dispersed across the cosmos with projections indicating that our Milky Way galaxy alone could contain over 100 million such objects. Although their elusive properties complicate direct observation, astronomers have recognized numerous potential examples within our galaxy, spanning from stellar mass black holes originating from the collapsed cores of enormous stars to supermassive black holes residing in galactic centers. The gravitational pull of black holes affects more than just nearby space, influencing the development of universal structures and the destiny of adjacent matter. Matter that drifts too close to a black hole meets a fate governed by its unyielding gravitational power. It is gradually drawn toward the event horizon, an ultimate barrier where it undergoes extreme gravitational stretching and is ultimately absorbed by the singularity at the center. The dramatic process called spaghettification is the intense result of a black hole's gravitational dominance. As an object nears the event horizon, the difference in gravitational pull across its structure becomes so extreme that it is elongated and deformed into a thin strand resembling spaghetti. The gravitational forces surpass the cohesive bonds holding the object together, disassembling it into a stream of particles that ultimately integrate with the singularity. Black holes present an extraordinary opportunity for examining the extremes of physics. They remain cloaked in mystery. The effort to decode their nature persists, fueled by a longing to comprehend the core aspects of space, time, and gravitational mechanics. Amid the vast expanse of the cosmos, black holes stand as quiet guardians, inviting humankind to delve deeper into the unexplored and broaden the frontiers of comprehension. Despite the immense remoteness from the nearest black hole, estimated to be around 1,500 light-year, questions and apprehensions regarding their possible effects persist. In 2021, scientists made a groundbreaking stride by obtaining the first definitive image of a black hole, specifically the one at the center of galaxy M87. The extraordinary feat delivered pivotal knowledge about black holes and their elusive form. The captured imagery showed that black holes consist of intricate layers, confronting the long-standing notion of them being isolated voids of absolute emptiness. Through detailed study and image compilation, researchers distinguish 3 specific layers within a black hole. The outermost is the event horizon, a vital boundary indicating the limit beyond which return is impossible. Once something passes this threshold, gravitational acceleration becomes unstoppable, sealing its plunge into the depths of the black hole. So what lies inside a black hole? Progressing inward, the photon sphere forms the second layer, a zone where light orbits the black hole endlessly. Any photons entering this area are overpowered by gravitational influence and remain eternally confined within the black hole's grasp. At the very center exists the singularity, the third and final zone where physical laws disintegrate. The familiar principles that govern space and matter collapse, ushering scientists into a domain of vast ambiguity and theoretical conjecture. The inherent intricacy and diversity of black holes pose major hurdles for scientific interpretation. Although many share a typical 3-layer model, every black hole has distinctive properties and actions that evade straightforward classification. Therefore, classical scientific methodologies often fall short when exploring these immense cosmic phenomena, demanding inventive and novel techniques for uncovering the truths, since direct analysis is not feasible due to the overwhelming gravitational constraints. Indirect monitoring remains the main approach for studying black holes. Any mission attempting to deploy instruments into a black hole would face inevitable obliteration by the extreme gravitational environment. So, researchers maintain their pursuit of understanding these astronomical titans. Numerous hypotheses, from stellar collapse to dynamic cosmic evolution, provide captivating insights into their origins and nature. NASA's observations of the central region of M87 uncovered convincing indications of a massive black hole influencing massive regions of space. Despite numerous difficulties, the drive for discovery moves forward, powered by the innate human urge to explore and explain. Although black holes may defy basic understanding, the enduring commitment to scientific discovery holds promise for unveiling the universe's darkest secrets. Roy Kerr's revolutionary findings in 1963 introduced a game-changing view of black holes by proposing a model of rotating black holes that challenged accepted doctrines. A cornerstone of Kerr's theory was the aerosphere, a surrounding region where opposing forces neutralized total gravitational collapse, keeping matter from plunging further inward. This unusual area exhibited remarkable deviations from standard physics, pointing to the deep puzzles buried within black holes. However, perhaps the most captivating outcome of Kerr's hypothesis was the suggestion of an Einstein-Rosen bridge or wormhole, speculative construct that could link distant regions of space or even parallel realities. The wormhole concept emerges from the sophisticated relationship between reality and the principles defined by general relativity. In this vision, reality is woven into a 4-dimensional tapestry called spacetime, which is warped by mass, creating the gravitational effects we observe. Wormholes are essentially shortcuts through this vast fabric, potentially joining widely separated locations in space and enabling rapid transit across the cosmos. So that structural integrity and usability remain contentious among physicists, while wormholes open up thrilling prospects for interstellar voyages and temporal experimentation. Serious barriers and theoretical inconsistencies dampen these hopeful visions. Their fragile nature, along with challenges from quantum theory and radiation, casts doubt on their functionality as transport mechanisms. Furthermore, general relativity sets hard limits on movement. Speeds through spacetime, implying that, even if wormholes were stable, they might not allow travel faster than light, a hallmark of science fiction. Nevertheless, wormholes continue to inspire scientific inquiry. The notion, named after their foundational theorists, embodies the thrilling idea of universal passageways and alternate dimensions, sparking humanity's imagination about the broader cosmos and its infinite potential. The ambition to forge a single unified explanation that bridges the gap between gravitational theory and quantum mechanics has led scientists toward a theory of everything, a total model that encompasses all elementary forces and particles. At the head of this mission is the celebrated physicist Moku, whose pioneering research has advanced superstring theory. This theory marks a profound shift from conventional paradigms by proposing that elementary particles are not tiny dots but minute, vibrating strings. These strings, similar to those on musical instruments, vibrate at unique frequencies, generating all known matter and forces. In this view, the universe resembles a grand composition with each particle symbolizing a specific tone of these elemental strings. Superstring theory may also illuminate some of the most puzzling features of black holes, wormholes, and other exotic elements within Einstein's gravity equations. The oscillation of strings through spacetime contributes to the emergence of singularities and topological oddities. Despite its beauty, superstring theory is extremely complicated and requires the existence of extra dimensions beyond the familiar three spatial and one-time dimension. These hidden dimensions, not directly observable, challenge human perception. To illustrate their elusive nature, analogies like fish living on a two-dimensional surface help explain how beings in a limited dimension might be unaware of higher spatial planes. The hidden dimensions are believed to be compactified or curled up, making them undetectable in daily life. They profoundly affect physical phenomena. Though their exact character remains undetermined, their theoretical presence offers valuable explanations for the universe's strange behaviors. Additionally, the mathematics behind superstring theory has sparked a revival in theoretical physics, revealing links between abstract math and the tangible universe. Indeed, the drive to discover a theory of everything has unified various scientific fields, highlighting the deep relationship between numbers and natural laws. However, superstring theory still awaits experimental support, as its predictions are hard to test due to the invisibility of higher dimensions. Even so, the bold vision of superstring theory continues to enthrall scholars and dreamers, urging humankind to pursue intellectual growth and cosmic insight. As we progress through modern physics, guided by this luminous theory, we stand on the edge of deeper knowledge and awareness. Decoding the puzzle of quantum black holes has long baffled researchers and remains one of the greatest puzzles in physics. Despite countless attempts to resolve this conundrum, a complete answer has proven elusive. Edward Witten from Princeton's Institute for Advanced Study famously called superstring theory 21st century physics that accidentally arrived in the 20th century. Yet, recent developments have reinvigorated hope. Multiple teams have independently unveiled major progress, indicating that string theory might indeed offer a full solution, though currently limited to simplified two-dimensional models instead of the 10-dimensional structure normally proposed by string theory. Although this marks meaningful advancement, a full resolution is still pending. The intricacies of the issue present major obstacles. The ongoing journey toward a unifying theory calls upon us to explore the farthest reaches of the cosmos, where the line between fact and theory blurs and profound revelations await. The study of black holes holds deep significance for our comprehension of the cosmos, challenging fundamental ideas of reality and prompting existential contemplation. The interaction between black holes and other celestial events like neutron stars and gamma-ray bursts reveals the delicate processes shaping our universe.